Hello, everybody. This week we have Raphaël Tinarrage, who will be talking to us about persistent Stiefel-Whitney classes.
Thank you.
Raphaël, we can't hear you.
All good?
I think so, yeah.
Take it away.
All right. Yeah. Is it okay? Oh, fine. All right. Thanks, everyone, for being here. I'm very honored to present this work. So it is called Persistent Stiefel-Whitney Classes. And the aim of this talk is to introduce Stiefel-Whitney classes. And then I will propose a way to estimate them in practice. So let's start with persistent homology. So all of this is based on persistent homology. And I like to present persistent homology like that. You have a point cloud X that comes from a scientific experiment or any acquisition of data. And you suppose that this point cloud X is sampled near to some submanifold. So I denote the point cloud X and the underlying submanifold M here is a circle. So it begins with the filtration of your space. In this talk, we only deal with check filtrations. So the thickening of X, the offset of X is denoted xt, the T thickening. And the check filtration of X, the collection of all thickenings, I denote it V of X. Once you have a filtration, you can consider the corresponding persistence module by applying the homology functor, and you can compute its barcodes, and you hope to read the homology of your submanifold in this barcode. However, as you may know, in some cases, homology is not a rich enough invariant to understand topology. I give here the example of the torus in the clay bottle over Z over 2Z, the field with two elements to distinguish between them. You could use other invariants from algebraic topology. For instance, the homology groups over a different finite field. Here, this will be enough to distinguish between them. You could use a more powerful invariant, the homology group over Z. So this is a bit of a nightmare, as you may know, in a persistent point of view. Something which is also interesting is the cohomology algebra. So these are the cohomology groups with an algebra structure added. But today we will consider Stiefel-Whitney classes. And I give here the simple example of the first Stiefel-Whitney class of the tangent bundles of the torus and the clay bottle. And these classes happens to be different. So we can discriminate between these manifolds thanks to Stiefel-Whitney classes. So this work, I try to make them persistent so we can actually estimate them in practice. So we will spend 10 to 15 minutes defining these classes. So this will be a great opportunity for you to interrupt me if you have any question. Then I show you how we can make them persistent, and we'll end with a discussion about algorithms. So if we want to talk about Stiefel-Whitney classes, we have to talk about vector bundles. I give you here the usual definition of a vector bundle. Over X, we have a base space, X. It is a topological space. A vector bundle over X is a surjection from E to X. So E is another topological space that is called the total space. And we ask for this surjection to satisfy two properties. First, the fibers, that is the preimages of points of X, have to be endowed with a vector space structure. And moreover, these fibers have to satisfy some local triviality condition. Basically, that means that we have a topological space X, here the circle, and on top of it, on top of each point, we put a vector space. So for instance, the normal bundle of the circle is defined like that. For each point of the circle, you put the tangent line, the normal line. This gives you a vector bundle. Another example, the Mobius strip. So the difference with the normal bundle, you can see that in the Mobius strip, the lines only do a half twist when we turn around the circle, while on the normal bundle, the line do a full twist. The dimension of a vector bundle is defined as the dimension of the vector spaces. So the tangent bundle of the sphere is an example of a vector bundle of dimension 2. You just put the tangent space on top of each point of the sphere. This construction works for any manifold. It does not even have to be embedded. If your manifold is embedded, you can consider another type of bundle, the normal bundle. For instance, here I have a torus in R3, and I can put tangent lines on top of it. And now we have vector bundles. We can define Stiefel-Whitney classes. So I give you here the axiomatic definition, and we will see later how they can be built. But it goes like that. If you have a vector bundle over X, you can define cohomology classes, particular cohomology classes, W0, W1, etc., that satisfy some axioms. W0 of pi, I will call it the 0th Stiefel-Whitney class of my vector bundle pi. It is an element of the 0th cohomology group of X over Z over 2Z. The first Stiefel-Whitney class, W1, is an element of the first cohomology group, and so on. I won't read all the axioms, but the first one is important. W0 is always equal to the unit of the cohomology group, the 0th cohomology group. And moreover, if my vector bundle is of dimension D, if I have vector spaces of dimension D, the Stiefel-Whitney classes are 0 when you pick I greater than the dimension. All right. So let me give you some insights about that.
I don't think you've defined bundle map yet, have you? You used an axiom too.
Yeah, I won't go through that, but
okay.
we should need some other notions to describe these axioms. If I have two isomorphic vector bundles, then their Stiefel-Whitney classes are equal. I didn't really define isomorphisms of vector bundles here, but it is important to understand that Stiefel-Whitney classes are not invariants of manifolds or topological spaces because they are not defined at the topological space level, but they are defined for vector bundles. So they are invariants of vector bundles. So here is the most important interpretation of Stiefel-Whitney classes. If my vector bundle admits a section, then the top Stiefel-Whitney class is 0. A section, for instance, if the vector bundle is a tangent bundle, a section is a vector field. And this is why these Stiefel-Whitney classes have been designed. at the beginning. And you can generalize this statement if your vector bundle admits k independent section, then the top k Stiefel-Whitney classes are 0. Right. And of course, they contain some topological information about your base topological space. For instance, if the tangent bundle I consider is a tangent bundle, I can read the orientability of my manifold in the first Stiefel-Whitney class of the tangent bundle. The manifold is orientable if and only if W1 is 0. And for those who like physics, my manifold admits a spin structure if the two first Stiefel-Whitney classes are 0. Okay. So in order to get a bit further in the theory, we have to describe the Grassmann manifold. So let us pick two integers. The Grassmannian GD of Rn is defined as the set of all the d-dimensional subspaces of Rn. And this set can be endowed with a topology and a manifold structure. And at the end, it is a manifold of dimension d times n minus d. So for instance, G1 of R2, this is a set of lines in the plane. It is on dimension 1, and it actually is a circle. G1 of R3 is a set of lines in the space. So it is a surface, a non-orientable surface. So let me show you how you can build G1 of R2. So you are in the plane, you have a line. Take the unit circle. This line intersects the circle in 2 points. So you can describe the Grassmannian G1 of R2 as the circle where you identify opposite antipodal points. But identifying antipodal points on the circle gives you again a circle. For the interpretation, at the beginning, the circle goes from 0 to 2 pi. But if you take the quotient, it goes from 0 to pi. All right. We will also need the infinite Grassmannian. So I denote R infinite the space of sequences of real numbers that are 0 from some point. And just as before, you can consider subspaces of this vector space. And this gives you the infinite Grassmannian of D planes of R infinite. And something great happens. The cohomology of the infinite Grassmannian can be really simply described. So the cohomology over Z over 2Z is the polynomial algebra generated by D indeterminates. They are called W1, WD. And each WI has degree I. So it means that WI is an element of the cohomology algebra. WI belongs to the ith cohomology group. In a particular example we'll use, when D is 1, the set of lines of R infinite, so it is simply the polynomial algebra with 1 indeterminate. A last fact we will need about Grassmannians, they can be embedded in the matrix space. So consider MRn the space of n times n matrices. Take any point of the Grassmannian, take any d-dimensional subspace of Rn, and map this space to the projection matrix on it, the orthogonal projection matrix with respect to some basis. This map is an embedding of the Grassmannian into the matrix space. So we can see the Grassmann manifolds as submanifolds of the matrix space. Okay. And now, thanks to the Grassmann manifolds, I can describe this correspondence that exists between vector bundles and classifying maps. So it goes like that. If say that you have a topological space X and a continuous map from X to the Grassmannian, then you can build a vector bundle structure on X. So basically, you just pull back the spaces of the Grassmannian on top of X. And this works conversely. If you have a vector bundle over X, you can find such a map, Xi, that goes from X to the Grassmannian, that will give you your vector bundle by pulling back. And this map is called a classifying map. So what is nice is that in practice, we can choose a classifying map that go into GD of Rm for M large enough. We do not have to consider the infinite Grassmannian, but simply the finite Grassmannian. So this is an illustration of the circle and its normal bundle. This bundle can be described as a map that goes from the circle to G1 of R2. In this case, R2 is enough. Okay, and now I can propose this other definition of a vector bundle. A vector bundle over a topological space X is simply a continuous map from X to the Grassmannian. And now we have this second definition, we can actually build the Stiefel-Whitney classes. So say that we have a vector bundle described as before.
Can I ask you a quick question?
Of course, yeah.
Sorry, just for the intuition. What would the picture look like if I wanted to draw Xi for the Mobius bundle?
In this case, this is really simple. You start with this point. Look at the angle of your line. It is 0, so it is mapped to 0. This one, for example, you have an angle of pi over 2, so you will go here. When you do half a turn, you are again 0. So this map actually winds twice around the Grassmannian.
Ah, interesting. Thank you for the explanation. Thank you.
Thanks for the question. Okay, so we have this map, this vector bundle structure, this vector bundle. I can consider the map induced in cohomology. I denote it Xi star. And this is a map from the cohomology of the Grassmannian to the cohomology of X, right? Now, recall that the cohomology of the Grassmannian is generated by these classes, W1, WD. And you will take the image of these classes by this map induced in cohomology. And this gives you the Stiefel-Whitney classes. The 0th Stiefel-Whitney class is the image by Xi star of W0, W0 being 1 in this algebra. The first Stiefel-Whitney class of Xi, W1 of Xi, is the image of W1, this cohomology class in the Grassmannian, and so on. So I propose an example here. As I explained, the map Xi that describes the normal bundle of the circle is a map that winds twice around the Grassmannian. But if you wind twice, your image in cohomology is 0. The induced map in cohomology is 0 because we are over the field Z over 2Z. So the image of W1 will be 0. Let me show you what happens with the Mobius strip. the Mobius strip, so you start here, is mapped to 0, and when you turn around the circle, for instance, if you are here, you have an angle of pi over 2, so you end up here, and then you continue. This map, psi, that describes the Mobius strip bundle, actually looks like the identity. It winds only one time. So its image in cohomology is the identity. And the image of W1 will be non-zero, it will be 1 in the first cohomology group of the circle. And as you can see, the first Stiefel-Whitney class here allows to differentiate between these two bundles. If you don't have question, I will start with a persistent point of view.
I have a question. So these Stiefel-Whitney classes, in some sense, sort of keep track of angles, in some sense.
Yeah.
Okay, that's interesting.
So in this case, these two bundles, they can be described with a map that goes into G1 of R2. And yeah, angle is enough here to describe them.
Okay, nice.
Okay, now we want to estimate these classes in practice. So we need a sampling model for vector bundles. I say that we observe a vector bundle if we observe a point cloud X, a subset of Rn, and a map that goes from X to the Grassmannian. So we endow X with a vector bundle structure with respect to the second definition. And as for persistent homology, we would like to define a check filtration of that. So let xt be the check filtration of X, the collection of all the thickenings of X in Rn. I would like to define extended maps, xit, that will go from xt to the Grassmannian, and that will give the thickenings vector bundle structure. Unfortunately, I didn't find any interesting way to define these extended maps. You could try to take a point of the thickening of X and project it on X, but this is really well behaved. We should adopt another point of view here. And actually, sampling, observing a point cloud and a map from this point cloud to the Grassmannian is equivalent to observing a point cloud in the product of Rn times the Grassmannian. If you have this model, just consider the set X check. You could call it the lifted set X check to be the set of pairs, one Euclidean point and the corresponding subspace. This gives you a point cloud in this product. And from now on, we will use this sampling model. And now it goes in 3 steps. First, embed the Grassmannian into the matrix space. So we can see this point cloud X check as a subset of the product of Rn times the matrix space. Now, this product is a vector space. You can endow it with any norm. And you can consider the check filtration of X check in the product. And now, in this product, you can define easily extended maps, xit. So take the T thickening of X check and take a point in it. So a point in the thickening will be a pair, a Euclidean point, and a matrix. And you will project this matrix on the Grassmannian. So the Grassmannian seen as a submanifold of the matrix space. All right, so this works, and this is a structure that I call the check bundle filtration. The check filtration of X check in the product, and these extended maps. And now we can define persistent Stiefel-Whitney classes.
A quick question.
Yeah.
Is the projection generically well-defined?
No, it is not. This is an issue that I will deal with in a few slides.
Okay, fair enough.
I wanted to keep it secret, but yeah, there is a bit of an issue here.
I apologize for ruining the theater. Continue.
All right, say, okay, we have X check, a subset of the products, and we can consider the thickenings and the extended maps. Now, for every T, the T thickenings is endowed with a vector bundle structure, thanks to the map psi T. And so we can consider its Stiefel-Whitney class. And I recall that the ith Stiefel-Whitney class of this vector bundle is the image in cohomology of the class Wi, which is an element of the cohomology of the Grassmannian. And I say that the ith persistent Stiefel-Whitney class of this set is simply the collection of all the Stiefel-Whitney classes of its thickenings. And yeah, as you've seen it, Helranan, there is an issue here. These maps psi T are not well defined. And this is because we project on the Grassmannian, and you have to be sure that your matrix does not belong to the medial axis of the Grassmannian, right? So actually there exists a maximal value of T max, such that these maps are well defined. Fortunately, we can compute this value T max in practice. So it simply is linear algebra. If you give me a set X check, I can give you the maximal value T max, such that the check bundle filtration is defined. So that's how it is. The persistent Stiefel-Whitney class is defined up to some value. Okay, I propose a summary of the information given by a persistent Stiefel-Whitney class. This is called the lifebar. Take a persistent Stiefel-Whitney class, a collection of classes. The lifebar of it is the set of values of T such that the corresponding Stiefel-Whitney class is non-zero. And what happens is that this lifebar actually is an interval. So it means that if your persistent Stiefel-Whitney class is non-zero at some point in the filtration, then it will be non-zero until the end, until T max. So for instance, here I computed the persistent Stiefel-Whitney class of these two bundles, the normal bundle of the circle. So I see it as a subset of R2 times R4, the 2x2 matrices, and its persistent Stiefel-Whitney class admits a lifebar, which is the empty set. The class is 0 all along the filtration. So this is consistent with the actual Stiefel-Whitney class of the normal bundle of the circle. If you take the Mobius strip, the lifebar of the first persistent Stiefel-Whitney class of it is the full interval. So the class is non-zero all along the filtration. Okay, and we have some results about that. A stability result, if you do not observe the full vector bundle, but simply a finite sample of it with potentially some noise, the lifebars are still closed. You can show that the lifebar are epsilon close, where epsilon is the Hausdorff distance between the bundles. So in this case of this noisy sample of the normal bundle of the circle, I obtain a lifebar, which is the empty set, just as the actual one. And this noisy sample of the Mobius strip gives me this lifebar for the first persistent Stiefel-Whitney class. And you can see that, yeah, this is consistent with the other one. At some point in the filtration, you observe a non-zero persistent Stiefel-Whitney class. And just as persistent homology, we can also prove consistency results. So I won't read that, but basically, if your sample is close enough to an actual submanifold endowed with a vector bundle, there exists a whole interval of the filtration where the persistent Stiefel-Whitney class is equal to the actual Stiefel-Whitney class. And so this can be seen also in the lifebar. So here I took a torus and its normal bundle. So this is a finite sample, and I obtain this lifebar for the first persistent Stiefel-Whitney class. And it is so I have a zero Stiefel-Whitney class all along the filtration. While for the normal model of the Klein bottle, it is non-zero at some point. And if you remember what I said about Stiefel-Whitney classes, I could use this information to say something like my first bundle is sampled near an orientable object, while the second one is sampled near a non-orientable object. Okay, so we can talk about algorithms now. So actually, these two results really are direct consequences of the definition. What is a bit more complicated to do is to build an algorithm that would give us these lifebars. So we have to talk about simplicial approximation. So I recall the context here. I observe a point cloud, X check, a subset of the product of Rn times the Grassmannian, or Rn times the matrix space. It also works. I consider its check bundle filtration up to the value Tmax, and I look at the ith persistent Stiefel-Whitney class. So it can be described again as the image in cohomology of the class Wi in the cohomology of the Grassmannian. I want to compute this class on a computer. So we will use simplicial complexes. I need a triangulation of the thickening and a triangulation of the Grassmannian. A triangulation or simply a simplicial complex that has the homotopy type of the thickening. So this can be done easily, as usual, by taking the nerve of my thickening. Triangulating the Grassmannian is a problem in its own, and I will talk about that in a few moments. But if we have triangulations of my two spaces, I can consider its topological relations, and this map between my spaces can be pulled back as a map between topological relations of the simplicial complexes. And I would like to find a map, a simplicial map between simplicial complexes that would describe this map here. I want to make it simplicial. So this is a problem that is known as simplicial approximation. And we know how to do that in algebraic topology. The solution is based on the star condition. So I will illustrate this condition on an example. Say that ST, the triangulation of the thickening, looks like this simplicial complex of dimension 1, and say that G, the Grassmannian, looks like that, and I consider this embedding G of ST. So this is an embedding of ST into the Grassmannian. Now, take any vertex V of the first simplicial complex. I say that the map G satisfies the star condition at the vertex V if the image of the closed star of V is included in the open star of a vertex of the second simplicial complex. If you can find such a vertex W for each vertex V in the first simplicial complex, the map G satisfies the star condition. And if it does, for every vertex V of ST, you can choose any corresponding vertex W. Such a choice is called a simplicial approximation. And you can show that a simplicial approximation is a simplicial map between simplicial complexes, and that it is homotopic to G, the first continuous map. So we solved the simplicial approximation problem here. If the map G does not satisfy the star condition, there always exists a way to ensure that it does, and it consists in subdividing the first simplicial complex. Okay. In practice, though, we cannot use this star condition directly. This is because we have to make sure that the closed star of V is included in the open star of W, but the closed star of V consists of infinitely many points, and we cannot do infinitely many computations. So I propose a weaker version of the star condition. So it is called the weak star condition, and you simply ask for the vertices of the closed star of V to be included in the open star of W. This can be computed in practice. So you can also define weak simplicial approximations. So for every vertex V, you choose a vertex W that satisfies the weak star condition. You can still show that a weak simplicial approximation is a simplicial map. And moreover, if my initial simplicial complex is fine enough, if it is subdivided enough, then the star condition and the weak star condition are the same, they are equal conditions. If my initial simplicial complex is subdivided enough, weak simplicial approximations will be homotopic to the map I consider. Okay, we had to talk about triangulations of the Grassmannian also. So Grassmannians can be triangulated. This is because they admit cellular structure, which is really well understood. So in theory, you can go from a CW structure to a simplicial structure. However, doing it in practice is not easy, and I working on it at the moment. So I wandered through the internet to find triangulations of the Grassmannian, and the only one I found was triangulations of G1 of Rn. So when D is equal to 1, the Grassmannian of lines of Rn. And so you can do it like that. You take a triangulation of the sphere, like the boundary of a simplex, you subdivide it, and then you just quotient the antibodal points. You obtain a simplicial complex that is a triangulation of the Grassmannian of lines of Rn. And so yeah, the algorithm I propose at the end is limited to the case D equals to 1. But if we had triangulation of general Grassmannian, we could try it So this is why the examples before were only for the first Stiefel-Whitney class of my bundles. Okay, so the algorithm at the end looks like that. If you want to compute W1 of xi, the persistent Stiefel-Whitney class at time t, you take a triangulation of your thickening, a triangulation of the Grassmannian, you subdivide ST until xi t satisfies the weak star condition. When it does, you compute a weak simplicial approximation, and then you take the image of the class Wi in the Grassmannian to obtain your persistent Stiefel-Whitney class. This is for computing the persistent Stiefel-Whitney class at time t. However, we would like to compute the filtration of it. We like to compute its lifebar. So this is the last slide of the talk. Let me show you how we can compute the lifebar. So the lifebar is a set of values of t such that the persistent Stiefel-Whitney class is non-zero. So to do that, we have to find this value here, when it goes from 0 to non-zero. We could do that by computing the class for several values of t and check whether it is 0 or not by a dichotomic search. We could use the persistent image algorithm that allows to compute the image of a persistence module. But in this case, there exists even a simpler way to do that. And it is based on mapping cones. So the mapping cone is a usual construction in algebraic topology. The mapping cone of xi t is a topological space that contains information about the map xi t. And the mapping cone comes with an exact sequence like that. And you can deduce directly the formula. The rank of the image of xi t in cohomology is this sum, which is actually finite. And we can actually compute all these terms with the usual persistent algorithm. Yeah, so this is what I've done. You can have a look on my webpage. I published a notebook to use these classes in practice. So a word about perspective. These Stiefel-Whitney classes are a particular instance of a more general theory that is called characteristic classes. And I think that these ideas could be used also for these other classes. And yeah, have you seen the algorithm is limited to the case d equals to 1 because I do not have access to any triangulation of GD of Rm when d is not 1. So this is something I'm working on it at the moment. If you have any ideas about that, I will be glad to hear. And this is the end. Thank you.
Thank you so much. So before we go to questions, I'm going to ask everyone to please unmute themselves and applaud the speaker.
Thank you.
Okay, so are there any questions for the speaker? Again, you can unmute yourself and ask, or you can post it in the chat.
Yeah, this is Ira. I have a question. So what I was waiting for is at the very end, you said you want to extend to the other characteristic classes, but you have to change your coefficients from Z mod 2Z to at least Z or real coefficients. How are you going to do that? I mean, that seems a lot of the hard work with trying to use this persistent homology, extending your coefficient ring. Any thoughts on that?
So to extend it on Z, I have no ideas. So R, you talk about R, the field R.
I'll take Z. I'll take Z. It's okay.
Z.
Okay. I mean,
Yeah. If you were only to compute the lifebar, you just have to check whether the class is 0 or not. So I think this could be more easily done than actually like knowing what exact class is the characteristic class. Do you see what I mean?
yeah, but usually this present homology, we only use Z mod 2Z. So now you're changing everything. That gets hard.
Yeah, clearly, yeah. This algorithm would not work here because in order to compute this sum, I simply use as a usual persistent algorithm, and this couldn't be used. Yeah.
No, I find this very interesting, and this is the question I was going to ask you, and you put it at the end. So
yeah,
all right, thanks.
I don't have precise ideas for that. Yeah.
Yeah. Thanks.
Could I ask a question / propose something? So if you had an algorithm to compute a representative cocycle for a Chern class, for example, you could reduce it. Like you could look at its image in the cohomology mod 3, mod 5, and whatnot, and see if you get 0. And if you don't, at least you know that it's non-trivial.
Yeah. Yeah. If you are able to yeah. So you could yeah. I agree.
And I have a question. Have you seen at these papers that, well, first of all, the talk was good. Thank you very much. And I think like this topic is really interesting. So thanks a lot for the talk. Have you looked at these papers where they give lower bounds on the number of simplices that you need to triangulate a Grassmannian?
Yeah, I've seen it, yeah.
So that looks kind of bad in the sense that the lower bounds are exponential.
Yeah. So this is something I dealing with right now. So if you know a bit about cellular structures, if you want to triangulate the Grassmannian, you could just triangulate the cellular structure of the Grassmannian. So what I tried last week is to build the Grassmannian by gluing cells on top of each other. And when I glue cells, I have to find simplicial approximations of the gluing maps. And yeah, I ended up with millions of simplices in order to satisfy these store conditions.
Right.
It's a bit of a problem, the number of simplices you need.
And in practice, the subdivision, is that a problem? Like, do you end up having to subdivide a lot or not?
Yeah. So to give you an idea, if you have a circle described by 3 points and edges, and you want to glue another circle on it, you have to subdivide it twice. If you have just for the map, the identity to satisfy the store condition, the first simplicial complex has to be subdivided twice. Yeah, and if you want to turn around 2 times, you have to subdivide it 4 times.
I see. Okay, thanks.
I had 2 questions. Raphael, really nice talk, really enjoyed it. So the first question, so, in standard persistence, if I just take my metric space and scale all the distances, then I know exactly what happens to the barcodes. But is that correct? Is it correct to say that's not the case here? If I scale my metric space, but I don't scale the metric on the Grassmannian, then the barcodes don't just scale linearly. Something more complicated happens to them. Is that correct? And do you know what that looks like?
Yeah. So at some point you have to pick a norm on the product. Where is it? Here. I say, for instance, here I took this really the Euclidean norm on Rn times the metric space. So the persistent Stiefel-Whitney class depends on this norm, but actually the homology, the persistent homology of the check filtration also depends on this norm.
Certainly, yeah.
So in the paper I wrote, I took the general family of norms with a parameter gamma here. So if gamma is 1, you have this norm, and when gamma changes, you observe very different behaviors of, for instance, even for the normal bundle of the circle, with gamma equals to 1, you see the homology of the circle. If gamma is greater than 1, you can see the homology of a sphere, of a 3 sphere at some point. So even the persistent homology is affected here.
Mm-hmm. And then one more question. So do these life bars, do they ever sort of appear, disappear, and reappear again, or are they always just one bar?
No, if they appear, it doesn't disappear.
And then I'm curious what happens if you have something like, like a torus knot on a torus. So like at one scale, your data set looks like a circle, but at another scale, it looks like a torus. Anyway, yeah.
Yeah. In this setting, you cannot erase non-orientability.
I see.
Yeah, you can say that vector bundles are non-orientable if they contain a Mobius strip.
Gotcha.
And this cannot be erased.
And so once it appears, it's there forever. Even if the Mobius strip fills into a disk, to a solid 3 ball.
Yeah, you still have a Mobius strip on the boundary.
I see. You can still flip it. Okay.
Mm-hmm.
Thanks. Very nice. Very cool. Appreciate it.
Thank you.
Can I also ask one very quick question? I don't even know if it's a question or just a thought. So I was trying to imagine a simple data set that would potentially come to you in the form of a vector bundle. And I was sort of imagining, like, if you had some like meteorological data and you had, say, a weather system, and you had, say, some local information about which way the weather was flowing, which I guess would be one-dimensional. Would that be the right kind of data to compute this for? Would that make sense to figure out, I don't know, maybe something about the winding of the vector field? Does that seem accurate?
Yeah. Yeah, of course. I was thinking about also in physics, when you not only observe a particle, but the particle endowed with its velocity. And yeah, same for your example. I think I can.
But your weather example is a trivial bundle, isn't it? There's no twisting in it.
So yeah, so in this case, if you just follow the tangent bundle of your
I don't know, maybe there's a storm with an eye in it. I'm trying to envision when things could become more complicated.
That sounds more like a section of a bundle. Like you're picking one vector in each fiber as opposed to a bundle.
Yeah.
But it's not non-zero.
If there's an eye of the storm, then it vanishes somewhere.
I hope that you can find some interesting vector bundles in nature. I should think about that.
I had one more question. How do you compare life bars?
Just by looking at this value here.
Because there are intervals, like you're looking at 0 to t max, right? What if t max varies?
What does Tmax?
You have t max over here, right? What if t max varies? It's like different. So in some cases you have say 0 to 1, some cases you have 0 to 0.7.
Oh yeah.
So you have different, right? So can you just scale all of them and sort of normalize it?
Yeah, in these examples, I simply compare bars with this value here, and yeah.
Yes. What I'm saying is, what if the values are different?
Could I compare the Tmax values?
Yeah.
Yeah. But I see. Yeah. In this example, for instance, the life bar actually does not go from 0 to 0.7. It goes from 0 to 0.65 because I have also noise in the matrix space. But I wouldn't want to compare these end values. I prefer just to compare this value here.
Okay.
I had a question as well as a comment. Perhaps working over the integers to try and understand Chern classes would be quite difficult, but if you work rationally or over the reals, then there's another construction of the Chern classes due to Chern and Vey, which really involves a lot of geometry that could be interesting.
All right.
Even though now you've killed torsion. My question, though, is there's another construction of the Stiefel-Whitney classes using Steenrod operations and the Thom isomorphism. And I'm curious if you've thought of moving in that direction at all in terms of like a persistent Steenrod operations.
Yeah. But this construction is designed for manifolds, right?
The Steenrod operation and Thom isomorphism construction?
Yeah. When you have
I'm not sure that
bundle,
it matters. It doesn't require a manifold.
Doesn't it?
No, you just use the Thom isomorphism for the bundle. You look at the Thom class.
Okay.
And the Steenrod operations exist completely generally.
Yeah, yeah, of course, yeah. I didn't think about that. Yeah, I thought, yeah, because you have also this construction of Stiefel-Whitney classes from a triangulation of a manifold. Like if you have like a triangulation, you have a formula for the Stiefel-Whitney classes of the tangent bundle. But here I wanted to have something very general that will work for any topological space endowed with the vector bundle. And I thought this construction you mentioned assumed that you have a manifold.
Maybe it does. I don't remember it. I just remember that was the construction that Milner and Stasheff used, but I certainly prefer this classifying map construction. I think it's much nicer.
Yeah, it will be very interesting just to have Steenrod operation or simply just cup products, because here, I mean, the life bar really is my class 0 or non-zero, but you have much more information in these classes than just the nullity of it. For instance, does the cup product of two classes is 0 or not? Or so I'd love to have algorithms that could compute cohomology operations.
Cool. Thanks again for the nice talk.
Thank you.